Okay, in this lecture, let's explore quantitatively the relationship between an image formed by a reflection off of a spherical shaped mirror from an object placed in front of it. And we'll start first with a concave spherical mirror. So that's a mirror that bows away from you, bows out, or it bows in if you like. It's concave. And if we shoot some light rays at it from the object at, we'll call it position P, we'll see those light rays reflect off of the surface and can form an image at a location which we'll call location Q. All right, now we're going to try to get quantitative, so we need to add some angles and some dimensions. Okay, it gets a little bit busy here on my diagram, but we can start with the radius of curvature. So we'll put at position C the center of curvature of this spherical shaped bowl-shaped surface, so that's kind of a bowl. It bows in, and that'll be radius r. And r will take to be positive number. So for concave spherical mirrors, r is positive. And okay, let's see how we can understand some relationships. But let me also first introduce the distance to the object. So the object's placed at position P, and from the vertex of the mirror, that is the location along the optical axis of this mirror. The vertex is where it meets the mirror, so that distance we'll call P, so the object distance is P. And the image that we want to locate, we'll put that at point Q, but that will be a distance Q from the mirror vertex here. Okay. And, well, if we put the object where it's shown here on this diagram, that's beyond the center of curvature, and more importantly, beyond the half of the radius of curvature, then it will form a real image for such spherical mirrors. So where it is, when it's larger than r over 2, it will form a real image, so that'll be on the same side of the mirror as the object, where that image is, and light rays are really going there. Okay, so let's now try to and understand this using some trigonometry and some algebra, how to solve for this location. So I've drawn a bunch of angles here. For example, we see the light ray that came out from the object reflected off the surface. The law of reflection holds, so the angle of incidence, theta here, equals the angle of reflection, which I also call theta, and then is focused down at position Q. But I've labeled a few other angles here. So in addition to theta, we have an angle alpha here. That's the angle the light ray makes from the object relative to the optical axis. And we also introduce an angle phi, which is the angle that the radius of curvature, or the line from the center of curvature, makes with that same reflection point here. So that's angle phi. And okay, we can look at a couple triangles here. So there's a triangle formed by P to the point of reflection to the center of curvature. So that triangle, angle alpha is shown here. Here's theta up there. And then this is an unknown angle, but we know for a line that's 180 degrees, and so the supplement to angle phi is this angle here, and so that supplement would be pi radians, or 180 degrees, minus this angle phi. So this angle in here, let me just go ahead and label it, that angle there is the pi minus phi, added to alpha and theta for this triangle I've highlighted here, and that has to add up to pi radians as shown here. Of course, we can then cancel or move cancel the pi, because that's on each side of the equation, here and here. And then we can also then solve for theta by just adding phi to both sides of the equation, and then subtracting alpha, and we get that theta is just, this theta is just going to be moving pi over the other side. Phi to the other side is phi minus the alpha. So we have this relationship for theta. It's phi minus alpha. Similarly, we can take another triangle. That's the triangle shown here with the angle phi, the angle theta, and then connecting down to where the image is at point Q. It has an angle beta I've labeled here. That's the angle from the ray coming from the reflection to point Q makes with the optical axis, so that's angle beta. So kind of go through the same sort of argument. The sum of the interior angles of a triangle have to add up to pi radians. So I can start here at position C, the center of curvature, and go to the point of reflection. This angle here is phi again. That's the angle that that line makes with the optical axis. I can add the upper angle here, this interior angle theta, that's the angle of reflection, again equals the angle of incidence. And then I add to it this angle, which is not shown, but it would be this angle there, and that'd be the supplement to angle beta. So I put a pi minus beta here for the supplement. And that sum has to again add up to pi radians for triangles. So again, we can cancel off pi on both sides. And then we can solve for theta by moving beta to the other side. Right? We can add beta to both sides and subtract phi. And so I get this relationship here, that theta is beta minus phi. And that's coming from this triangle, the second triangle, whereas the first relation comes from the triangle just outside of it. Right? So I have two relations for theta, which means I can eliminate theta by just setting those two expressions equal. So I can have phi minus alpha equals beta minus phi, right? By just moving and setting that equal on the top equation. Both equations have a phi in it, so I could consider adding phi to both sides, right? I can add phi and cancel on the right side, and add phi here makes it 2 phi. And if I do so, I get 2 phi equals, and what do I have left? I had the beta that was on the right side, and I could have moved the alpha over, and I get alpha. So twice phi, and phi was this angle that the line makes from the center of curvature to the reflection point, is equal to alpha plus beta in my diagram. This angle here and that angle there. Okay, so we have that geometric relation. Now let's relate it. How do I calculate, say, these angles from some of the positions I know and lengths I know? For example, I introduced the length or the distance the object is in front of the mirror vertex, as well as the image distance, the P and the Q. So let's now relate these angles in terms of those dimensions. So let's look at the alpha, the first angle here, that is from the angle from the optical axis to the point that the object makes with the reflection point. The tangent of that angle, tangent, would be the opposite side length of a triangle, so let's call that height h here, divided by the distance for that point h intercepts the optic axis to that object point. So tangent of alpha is h, the height, over the object distance p, but we have to subtract off a little bit because this curved surface, this delta, this small value delta, is the distance where h meets and makes a perpendicular angle with the optical axis. Delta is that extra distance, and I need to subtract that in my tangent, so it's h over p minus delta. Similarly for beta, that's this angle here, tangent of that angle again is the same height h over the little distance here at the bottom leg. So that's the image distance q, which is a positive number because it's a real image, minus again that same length delta. So I've got tan alpha is h over p minus delta, tan beta is h over q minus delta. And what was one of the other angles? Phi, right? Phi is in there. So tangent of phi, again, tangent of phi is going to be the height here of this triangle, this opposite leg, h. And then what's that distance? Well, the distance to where the angle phi is measured is the distance to the center of curvature. So that total distance here is just the radius of curvature, just like it was the distance to the point of reflection. So that's r, but again, I have to subtract off that little bit delta. Okay. All right. So here's the point where we'll start to make some approximation. We're going to consider small angles. Okay, so what does that mean? Well, if I consider small angles, or also known as the small angle approximation, what does that mean? That can mean, for example, that when I take the tangent of that angle, tangent of alpha, that of course equals sine of alpha over cosine of alpha. But what that is going to go when alpha becomes small, cosine of a small number basically becomes 1, And sine of a small angle basically becomes that angle. So it's going to become alpha. So that's one consequence of considering small angles. The other consequence is this distance delta here, the extra amount from the vertex of the mirror to where we're measuring this perpendicular side of the triangle, that distance is going to go to 0. So when we take small angles, delta is also going to become very small. And so what that lets me say is that, for example, this first relation, tan alpha is h over p minus delta, the delta will go to 0, so I have h over p, and tangent alpha essentially becomes equivalent to alpha in the small angle approximation. So alpha goes to h over p. Likewise, beta goes to h over q, and tangent phi becomes phi, and that becomes h over r. So I have these relationships here. And so this all happens in the small angle approximation, which means the angles have to be small. So only light rays close to the central axis of the mirror. And those are known as paraxial rays, or paraxial light rays. So although I've exaggerated the angles in this diagram, they're going to be very small along the axis. So we're only talking about reflections very close here, near the vertex of the mirror. All right, well, if we do that, then we can write out this relationship above, right, the one here, and use this now definitions for these angles. So if we do that, here's what we get, right? So let's look at here. We have twice phi, where phi was h over r. So twice phi would be 2h over r. And let me put that on the right side of my equation, even though it was on the left side here. And now let me put in alpha and beta. What were alpha and beta? Alpha was h over p, and beta was h over q. So h over p plus h over q, that's the alpha plus beta. And that equals twice phi, which is twice h over r. So there's that relationship now expressed in terms of these distances, right? The height from the optical axis to where the image or where the reflection occurs on the mirror, and the object and image distances p and q, and the radius of curvature r. Of course, immediately we can see that, well, wait, every term contains an h, so I can divide it out. And then I have this nice formula shown here in the box that just 1 over the p plus 1 over q is 2 over r. In other words, 1 over the object distance in front of the mirror vertex plus 1 over the image distance in front of the vertex is 1 over half the radius, r over 2. And this was for a concave spherical mirror, and we consider r to be positive, and so this is our relationship now for the object and image distances in terms of the radius of curvature of that concave spherical mirror. Now, the object and image distances are p and q, so this is really a relationship of reciprocals. 1 over p plus 1 over q is 2 over r. Okay, so stay one more time. That was for a concave spherical mirror where the surface bows in, away from you, so it's kind of a concave bowl-shaped reflective surface. What about the opposite case? What about a convex surface, which bows out toward you? We can do that too. So let's go through that a little bit more quickly, because we're going to do a lot of the same sort of trigonometry and methodology. Okay, so a convex spherical mirror. We want the object-image relationship. So here is my convex mirror surface, so now it bows out toward you the object. And so for such mirrors, the image you'll form will always be a virtual image. It's going to appear to have emanate or be located behind the mirror surface. Of course, light rays can't really reach behind this mirror surface, so it's a virtual image there. All right, so here's my light ray coming from the object, reflecting with the law of reflection out away from you off this convex mirrored surface. So in that case, we can see, yeah, okay, we're going to have a virtual image. It looks like the light rays emanated from inside behind the mirrored surface. All right, again, the radius of curvature is going to be r, and I've drawn a bunch of angles here. So the radius of curvature is measured with respect to the center of the spherical shape, so that's now behind the mirror surface. And so that's R. And we again have an object distance P. That's the distance the object is in front of the vertex. So the distance from the mirror surface to the object. And Q, the image distance from the mirror surface to where the image is. It's a virtual image. So that distance Q we treat conventionally to be negative. That denotes a virtual image. So Q is less than 0. We may need to use absolute value, however, later. We'll see. Okay. So let's do the same thing where we define some angles and we look at the relationships to explore how the image distance Q and the object distance P are related. So I've drawn a few angles here. I've labeled them also with angles like alpha, beta, and phi. Angle theta will still be the angle from the law of reflection. The incident angle is theta and the reflected angle is theta. So okay, in this diagram here, I've labeled a bunch of angles, and we can work through some triangles and see what relationships we get. So we could start, for example, with one that allows, or includes, I should say, angle phi here. This is the angle that from the center of curvature to where the reflection occurred on the surface of the mirror with respect to the optical axis. So I've got this triangle I can show here. I've got phi radians from the bottom right angle, and then I have theta. This is the angle of reflection and incidence. I get that because I can see that angle theta was out here with respect to the perpendicular to the surface, and by alternate interior angles, that angle theta is the same angle theta over here inside my triangle. So that's theta. And then I have this angle, I'll draw it again kind of over here in purple. That's going to be the supplement to angle beta. So pi radians defines a line, pi minus beta would give me this interior angle inside that triangle. So pi minus beta. And the sum of the interior angles of a triangle, again, have to add to pi radians, and so that's this relationship here. What I can see is, again, I have pi on both sides of the equation. I can eliminate that. And if I solve for just angle theta, I can move beta to the other side of the equation and phi to the other side of the equation. So I have to add beta and subtract phi, and I get this relationship that theta is beta minus phi in terms of those angles. Okay. Likewise, I can pick another triangle. Let's take the one from the object now, which has angle alpha. That's the angle from the optical axis to the point of reflection on the mirror surface. I can add to that angle phi. So I'm talking now about this large triangle here. So here's angle phi that I'm adding. And I need the upper angle here for this large triangular region. So I have alpha, I have phi. What is this angle? There's a number of angles listed in there. Well, I know that it's going to be the angle basically along this, from this line, coming out along from the center of the curvature out to the reflection point. I would continue this way, but I've got to subtract off this angle theta. And that defines, I'll draw it in green here, that total interior angle there. So pi minus theta, minus this extra amount, would be the supplement. And that's this angle in this upper angle of this large triangle here. So I have alpha plus phi plus pi minus theta, and that has to add up to pi for it being a triangle. Once again, the pi's cancel on both sides. I can then solve for theta by moving theta to the other side of the equation, and I have that theta equals alpha plus phi using that larger triangle as opposed to the first triangle, which was the one inside to the right. Okay, two relationships for theta. So I can eliminate theta by setting those equal. Right, so I'm going to set that equal to alpha plus phi. And if I do so, then I can get a new expression. Again, I can move phi to the other side of the equation here. This phi moving over, I get twice phi. and then that has to equal beta. And then if I add these two equations together, well, basically move alpha to their side, I have beta minus alpha. So twice phi is beta minus alpha from this convex spherical mirror relationship. All right, now playing the same trick we did before, we can relate those angles to measured distances. We can talk about the height h. That's the height from the optical axis to where the reflection occurred on the mirror surface relative to this optical axis, as well as distance is p, that's the object distance in front of the mirror, and image distance q, that's the distance from the mirror to where the image is formed. So I can look at the similar relationships. Tangent of alpha would be the height here, h. Let me call that h. I know I've kind of wiped that out there, but it's underneath there. That's the height to the reflection point. And then over p, but I have to add a little bit more, so let me add inside here delta. That's that little extra distance beyond the mirror to where the perpendicular line intercepts the optical axis. So p plus delta, so that tangent of h over p plus delta, tangent of alpha, sorry, is h over p plus delta. So that's this relationship here. What about tangent of beta? That's this tiny interior angle here. Tangent of beta, again, is the same height h. And then it's over the image distance q minus that little bit of extra distance. We don't want to count the delta. But we have to be careful here. Because remember, the image distance for a virtual image is assumed to be negative, or the conventions take it negative, so it's less than 0. So I really want minus q to take the magnitude here of that distance q. And then I have to subtract off that extra amount delta I don't want to count. And then finally for phi, tangent of phi is going to be the height h, and since that's the angle measured with respect to the center of curvature of this spherical mirror, the total radius r is the distance to the surface, and if I subtract that little amount delta, that's what the tangent of phi is. It's the height over r minus delta. Now, again, we're going to consider small angles. So it's a small angle approximation. Again, in that case, delta is going to go to 0, and that means things like tangent of alpha just become alpha, and tangent of beta, beta, and tangent of phi, phi. So when I do all that, we see that my tangent of alpha just becomes alpha equals h over p when I ignore delta, and tangent alpha becomes alpha. Beta just becomes h over minus q, and phi just becomes h over r from the tangent of phi. So same trick before, we're doing the small angle approximation. I'll just write it down. Small angle approximation. All right, now we have these relationships for the angles in terms of those distances. So we have our object and image distance p and q. So let's take our relationship here that we had above, 2h is beta minus alpha. Again, I'll reverse the order, so we'll have beta minus alpha. So what was beta? Beta is minus h over q, so there's minus h over q. Well, actually, it's there. Sorry, there's the beta, minus h over q. I also have the minus alpha, so what was minus alpha? Alpha is h over p, so I have the minus h over p. So I wrote this as the other way around, minus alpha plus beta, but okay, you get the idea. Minus h over p minus h over q is beta minus alpha. And that has to equal twice phi. Phi is h over r, so that's 2h over r. over r. Okay, so what do I see here? Each term had h, which I can cancel out. And I've got negatives in front of both terms there. So I could multiply through by a -1. That would turn this to be plus, but put a minus in front of this. So that leads me to 1 over p plus 1 over q is minus 2 over r. But that's assuming r was considered positive. We'll take a convention where for convex mirrors, like this mirror here, which bows out to you, if the radius of curvature is considered to be negative, in that case, if r is considered negative, I absorb the negative into the definition of r, and I get rid of it in the equation. I have 1 over p plus 1 over q is 2 over r, and that is actually the same equation we had before for concave mirrors. The only thing we had to remember is that for virtual images from convex mirrors, q is negative, and that the radius of curvature for a convex spherical mirror is considered negative. So it's the same formula as for the concave expression. That's very handy. You just have to remember this relationship, that 1 over p plus 1 over q is 2 over r. Okay, so now we've done concave and convex spherical mirrors. But in the case using a small angle approximation, we'll treat separately in lecture what to do when we can't assume small angles. One final thing to talk about is this 2 over r on the right side. So let's quickly talk about that before ending this lecture. And that is the focal length of spherical mirrors. Okay? So let's let our object distance be infinitely far away from the mirror surface. So I put the object which was in front of the mirror so far away, it's going to infinity. Then in that case, a parallel plane wave is then reflected to converge at a single point. So I've got rays of light that are coming from infinitely far away over here to the left, going to reflect off my mirror to an image, so to form an image. So let's see what happens. My light rays come in from infinity. They're essentially so far away, the source anyway is so far away, they come in parallel to the optical axis, reflect at the mirror surface to a location to form an image. Which I think you see I've already labeled there. But we can understand what's happening there from our image object relationship, that 1 over p plus 1 over q was r over 2. We're letting p go to infinity, so 1 over infinity means that this is going to 0. So I just have that 1 over q becomes 1 over what we can call to be the focal length. But to equal the equation that we just derived, that focal length f has to be r over 2. So I've written it this way, that 1 over q plus 1 over p, and 1 over p went to 0, but 1 over q becomes 1 over f is r over 2, so this becomes 2 over r on the right side. And so that's what we're going to call to be the focal length of our spherical mirror. And that lets us write an expression then that just which will be similar for mirrors, for lenses, that 1 over p plus 1 over q is 1 over f, where f is r over 2 for spherical mirrors. And remember, use the convention that r is negative if it's a convex mirror. Now, just to point out, this was solving for the image location when we had an object infinitely far away, so that light rays came in from infinity basically parallel to the optical axis, and they were focused, and they have to focus actually at an image point q that is half the radius of curvature. But interestingly enough, the inverse also happens. I can have a light ray leave the location here at r over 2, and then come up and reflect and go out, and it will become a parallel beam of light. So the inverse also happens. The light rays can be reversed in direction. So if I have a bright light here at the center in front of this spherical mirror at r over 2, it will emanate an outgoing beam of parallel light waves. So an outgoing spherical wave at the focal point, so like a flash bulb going off here, will become an outgoing parallel plane wave, like in a flashlight beam coming out. So anyway, just an interesting point and usage of such a spherical surface. But the point here was to relate the r over 2 we got in the previous expressions for 1 over p plus 1 over q, that equals 1 over f, where f is defined to be the focal length of the spherical mirror, and it's r over 2. Okay, that ends this lecture showing how to get the image and object relationships for spherical mirrors.